using sort of a whirlwind crash through the Google Engineers Udacity course, which is free. So you should be able to, go through linear regression, logistic regression, linear models, gradient descent, stochastic gradient descent, and it's the whole shebang. Long short-term memory and generative models, the whole thing. So that's just background lectures. So it should be about CNNs, convolutional neural nets, and autoencoders and so on. And then once you get the basics from those lectures, you can start with this is all. So it starts with feed-forward neural nets with Keras, which is a sort of a wrapper on top of lots of deep learning libraries, and then it's mostly TensorFlow based shop.
Do we find it on your page?
It's on this. So this whole 360 and 525 is actually a sub-module of this other thing, which is a book we are writing, actually. So it's called Scalable Data Science from Atlantis. So because we're in Atlantis, right? So it's and in fact, student projects from this course, they're all already book chapters in the course. This is from last semester. And we are working on a Git book. The Git book currently is broken because I broke the maximum MBs allowed in Git book public version. So I have to find a shunt out of it, but basically it's also available as a Git book, all the content here. So it has the geospatial stuff, and the 360 modules go deeper into a lot of these areas, right? So, for example, so this we didn't cover. T-digest, we need T-digests. So this is when you want to have some score that's coming out of an algorithm that's helping you monitor an alert for an event. It could be fraud detection or anomaly detection for predictive maintenance operations with sensors. So there's a bunch of stuff here that's we haven't covered in 360, of course. This is a full semester course. But anyway, that's there if you're interested. Okay, so let's continue. So we were looking at so sorry I had a brain fart, but the second derivative of the log likelihood function, the slope equals 0 should be negative. So anyway, here is so we use var as our main type to start doing symbolic expressions. So let's say x is 1. We know that this is going to be of sage types, like integer rings. But then if you do var x, this is going to be, say, symbolic expression, right? So we briefly saw this, and you can check out the help for a var. So it's a symbolic variable with name, and then we're going to use the solve method to symbolically solve when we can. We do this by hand, but sometimes it's easier to do it with this computer algebra package because some expressions can be very complex to do by hand. So a lot of research mathematicians use these solvers. So let's try solving a simple example. So x squared plus 3x plus 2 equals 0. So we want to solve for x. So what are the zeros of this equation? So this is exactly how you do it. You put the expression here, and then a comma, and then the variable you want to solve in terms of. So it says x is minus 2 or x is minus 1. So that makes sense, right? 4 minus 6 plus 2 is 0, and 1 minus 3 plus 2 is also 0. Okay, and then if you have coefficients, say ax squared plus bx plus c, then you just have to declare all 4 as variables. You can just throw it into a string, x space a, b, c, and then simply solve for the values of x with unknown coefficients. So you get all of this for us. Right? This is the familiar quadratic. Okay, so then we can also solve a system of equations for several variables. So if you have x plus y equals 6 is the first equation, and x minus y equals 4 is the second equation, you can do a system of equations in a list like this. This is double equality symbol for symbolic equality. And then now we have two variables x and y, so we want to be solved simultaneously. So when x is 5 and y is 1, that equation is satisfied. It's a baby easy one, makes sense. So sometimes it will not be able to find the exact solution. It will just give you some identity back at you. Sine of theta, cosine of theta. This is, oh, that's the breaks. Okay. So the other very useful function is find root. This is actually a numerical solver, right? So it basically will, in this case, it'll use the search method basically to find the root. So you're interested in the root between 0 and pi over 2, and it will do a bisection search numerically to find it. So I think, so let's check. Numerically find the root of f on the closed interval AB. Possible where f is a function in one variable. This function only works in fixed machine precision. It's not possible to get arbitrary precision approximations with it.
Can you solve derivatives with solve?
Yeah, I think we have some examples of derivatives soon. So let me just see what this one is. So I think it's the bisection search. So sometimes you have to actually go and open the source code to see the details, or look in Sage Docs, which has much more information. So now we can do a bit more. So this is your question. So if u is variable u, I want to differentiate sine of u with respect to u. So sine, let's go sine of u, derivative of sine u. And I can also do, say, sine x squared. But I'm interested in the fourth derivative of x squared, so I'll put a 4 after x, right? So that's d by dx to the fourth of sine of x squared. And this, yeah, you just sort of look here for how I did this. There's more examples here. So now what about partial derivatives? So this is when you have x and y as two variables and you have a function, say x squared plus 17y squared. So that's not too bad. That's just sort of cup, a bowl sitting on the xy plane, blown up by 17 for the y squared quadratic form. So then when we can differentiate it, I'm interested in differentiating f with respect to x. So I'm only looking at the on the x side. You can do the same y. So here's differentiating with respect to y. So, and it can be fairly complicated, these expressions, but if it's too complicated, then you get a big mess back. Okay, you can also do integrals. So this is indefinite integrals. Okay, so that's a bit of symbolic expressions for calculus. So now let's use this for the maximum likelihood estimator, just to keep things back to where we were. So I have my theta, n, and tn as my variables, and then my log L is my expression now because this is the Bernoulli's log likelihood function for my statistic tn, which is the sum of xi's, number of ones. And then I can take my log L, log likelihood, and do a dot diff, find the derivative with respect to theta. And then now I ask what is d log L, so that's just what we were doing earlier by n minus tn over theta minus 1 plus tn over theta. now I can solve for it, right? Because I want the d log L to be 0. So find me, so solve that equation, and it just gives me theta as Tn over n. And you can also find out the double derivative at that point and make sure it's negative and so on. Yeah, so it's a bit of a magic, but you know, to properly understand what's happening in this sort of computational algebra, you know, do much more advanced courses, computer algebra. So this is just for you to try later, you can play around. So it's quite useful for your own research, so on. So what is the justification for this maximum likelihood estimator? It's the so-called maximum likelihood principle. So to understand this, let's look at it, instead of looking at all values of theta and 0, 1, let's just look at 3 coins. So there's an oracle or whatever, some gypsy person that has a bag with 3 coins in it, and each coin has a different weight. And she just gives you one, and you know, you toss it as many times as you like and give it back to her, and you have to guess which of the 3 biased coins she gave you. It's a very simple conceptual problem. So let's say, to be very precise, let's say the oracle has only these 3 coins with weight quarter, 3/4, and half coming up heads or ones. So the experiment is the following. So I'm basically, you know, my game is, I have to figure out, is it coin 1, coin 2, or coin 3. So my experiment is x1, x2, x3. So only 3 tosses. Let's say it's IID Bernoulli theta star. But theta star now is just one of 3 possible coin types, right? 3 possible coins: quarter, 3/4, or half. So that's the finite version of the problem. So then, suppose your results for your 3 tosses were, first one was head, the second one was tail, the third one was tail. Then our MLE will be 1/3, right? Because it's just sum of heads divided by sample size. And so, so the question is, what is theta 3 hat? Okay, theta 3 hat is 1/3, but it doesn't belong to any values that we know the coin is supposed to be at. Right? So you know, if we have a finite set of possible values for theta, then going after the MLE may not be the best idea, because our derivation assumed that theta lives in the space of all possible thetas between 0 and 1. So every possible coin was allowed. So in this situation, what we do instead is basically not just apply this maximum likelihood estimator cooked up for all biases, but to do this explicitly for each coin. So now the likelihood of coin number 1 with sample size 3 is going to be 9/64. Okay, and right. And for the coin 2, we just march through and put the second coin's probability of coming up heads, which is 3/4, and that's 3/64. And for the third one, it's 8/64. So we are just basically adapting this idea of you know, likelihood to just 3 values. That's all we need to look at. So now the most likely coin is you know, 9/64, right? Coin 1 with bias of 1/4. Yeah, that's all we can say with 3 tosses using this principle. Does it make sense? So, and of course, the idea is that when we toss it many times, this should hopefully converge to one of these 3 values, unless the oracle is messing with us, giving us something more dubious. Right? And also, it illustrates the point that the model is really in our head, right? So we are trying to, and it could be wrong. What we are trying to model could be very different from our assumptions, and that's something you have to always bear in mind. That's good for statisticians and data scientists, right? It's job security. So anyway, maximum likelihood and exponential lambda random variable, same idea. So we now have our likelihood function, which is lambda e to the minus lambda x. I mean, the density is lambda e to the minus lambda x. And so to get the likelihood, remember, it's just proportional to joint density. And if it's an IID experiment, the joint density is just the product of each individual marginal density. Okay. So we just basically do exactly the same thing. Now, this is a typo here. I don't know. Ignore this. Yeah. So basically, your maximum likelihood estimate will be simply the product of. So let's do this. Control. So let's write this down. So what's going to be the likelihood function? So we have n observations. It's coming from f of x lambda, where this is simply lambda e to the minus lambda x, right? So then the ln of all my data points as a function of the parameter lambda is simply the joint density, right? So normally it will be this. Because I have a realization, I can just, I want to think of it as a random thing, I can do it this way, semicolon lambda. And then because of the ID assumption, this breaks down into the product, right? And for us, each one is just lambda e to the minus lambda xi. Okay? And then if you take the logarithm, right? If you take the log on both sides, so this will be just the sum as I goes from 1 to n of the log of lambda e to the minus lambda xi. And you can rearrange this. So yeah, and using some properties of exponentials and so on, you're going to get this now, right? Because Tn is now the sum of the xi's, and so so basically you can break this into log of lambda plus log of e to the minus these things, and then because of properties of exponentials, you will get this much simpler expression, n log lambda minus lambda Tn, where Tn is just the sum of the xi's. Now this is just the sum of the samples, and this is not 0 and 1. This is just actual exponential realizations. Okay. So then to find the MLE, remember our lambda now lives in the positive reals. So to find the MLE, we simply differentiate this with respect to lambda and see how that looks. So that looks like lambda to the n minus 1 times n divided by lambda to the n minus Tn. Okay. So when we rearrange this, we find that the maximum likelihood estimator lambda n hat is n over Tn. So this is now, I'm just working with realizations. So, and then this is the realized point for the maximum likelihood estimate. And if you think of this as so this is bold lambda hat. This is how you would think of it as a random variable. So it means every time you repeat the experiment, the lowercase tn will have different realizations. So this is the random variable, which is our maximum likelihood estimator. Okay, so, and this is just, you can just solve for it, setting it equal to 0, and you get n over tn. or do it by hand because it's pretty straightforward. Now let's look at the New Zealand earthquakes. So here, the processing timestamps and floats with try-catch is what we're going to do in step 1. And then in step 2, we'll apply the data to our MLV and see how well this exponential product model with the unknown parameter lambda star can be estimated. Okay, so that's the main idea. So here is the files. It should be earthquakes.csv file I downloaded last week. And we should have 21,017 earthquakes from the data set. So later on, we'll look at rainfall in Christchurch data for the Markov chain, dry wet Markov chain. Okay, and remember that this is the first 3 lines, so these are the events, and so we're interested in origin time, longitude, latitude, magnitude, and depth. So these were the 4 things we were trying to play around last time, so I thought I'll wrap it all together and grab everything this time. So handling timestamps in Python in a big hurry, you want to dive further into these two. You want to dive further into these two. Docs, but let's just quickly go here. So from date time module, import date time. So this is what we're going to use. So first, let's create something called string dates, which is a list of these very simple strings. So this is month, day, and year in sort of this American format, right? The slashes. So often you will see timestamp data in some weird format, whatever it is. Especially Americans put month before year, whatever day, month before date, and so on. So you want to know a little bit about how to customize date time stripping to proper, special formats. So this is one example of such a format. So what we do is we do date time dot strip time method, and then you pass in TS. So TS is being a list comprehended from this string dates list we made. So for every TS in this string date list, I'm going to do my date time strip time of the timestamp with respect to this. And then if you chase these docs, this one, there's a big table that tells you where I got the percent lowercase m, percent lowercase d, percent capital Y, all of that from. So these are all very specific formats. And then the slash are there because the slash is in this sort of strings, the structure. So you can do random things because sometimes people put dash and sometimes people add colons before the time the hour starts and double colon before the second or whatever. So all that is fieldable. So then this just gives me these date time objects, right? And look, it stripped already the year, month, day, and then it puts 0 and 0 for hour and minute. So then we want to convert these datetime objects into a number. This is the sort of Unix time number, which is the number of seconds elapsed since 1970 Jan 1, I think. And so for that, we import time. It's another module. And then we do this dot make time thing. So now I'm doing this dot make time to this date times list I just made by comprehending with strip time. So now this just gives me these floats or these. So this is the number of seconds elapsed, which is very useful because now we have everything in one, sort of, like all the events after 1970, at least in this format. So now it's just doing it all at once, so we don't have all the bits and bobs floating around. Okay, so so this time tuple thing is what needs to be done to the DS before make time can be called on it. Now, I was just hoping like, okay, I want to auto-convert and not worry about it. So this is a really great, another thing, hunted down, just Google searching basically on Stack Overflows and stuff. So dateutil.parser is a nice parser. So you import parse from that module, and then you can simply hit parse with the timestamp of string dates. We're going back to the original string dates. see if it'll magically work, right? So it's supposed to auto-convert from a lot of standard formats. And for me, this automatically figured it out and is giving me the right answer. So I'm going to run with it instead of doing all this other stuff. Okay, then why did I do all this stuff? Well, because when the autoconvert doesn't work, you will need to specify your own string formats and extractions. So it's important to keep those cells to save time in the future. So here is now our New Zealand earthquake timestamps, right? This is how it came. This is the first one. So I want to see if I can just call parse on it. And I was hoping, oh my God, yeah, it worked. So it's, I'm not going to dig any deeper. It seems to pick up exactly what it is. 2018, month is 5, the month day is 17, right? Time in hours is 12. So this capital T is giving you the time, minutes. Yeah, everything seems to be coming out nicely, right? Yeah, and then there's some information about the, I don't know, ISD.
It's time zone.
Yeah, it's a time zone thing.
Yeah.
Okay, good. So yeah, that's what that is. And then now so I can just use parse, and so I'm just trying to do 2, just to be paranoid. Okay, it works on 2. Just a simple list comprehension. So I want to put everything in one go now and make sure that it works all nicely. Yeah. Because now I'm also applying that to my make time parse ds tuple time thing to get the number of seconds since 1970. So it's all good. So what I now need to do is, okay, now I need to suck in the full CSV file. So this is what Mahmoud was showing us last time with open date earthquake.csv sf reader f.read and data list. So now we're splitting the whole string of the whole file by end of line characters. So each line, each row ending in end of line is its own row basically. So it's 21,018 such things. So let's look at the first element of this data list. So that's the header. Second element is just the first data point, right? Great. And then it looks like the very last element is an empty line. So we just observe this and feel this instead of getting into special try catches for that. So yeah, but the second last line is okay. So so this is the same as -1, right? Okay, so now I'm going to so I'm going to have all my imports in one place. So I'll have my daytime and time and day-tuple parser. And then now that I have my data list already sucked in, so I'm going to go from the first element, which skips the 0th index, right, the header, and to the line before the last line, which is the second last line. So Mahmoud had this as well last week. And then now I'm just having my data row where I split by comma, because this is a nice comma separated variable file. And then I'm going to take this third element. Remember, the third element was the origin time of the columns. So I'm going to use 2 to pick the third element of the row. And I'm going to put that into my time string. So this is just a pure string that I need to mess with. And then I also create another one called my data string, just like homework from last time or whatever classwork. So for this, I'm picking 4, 5, 6, and 7. This is the long, lat, magnitude, and depth. And so now I'm going to try my type time is time.makeTime, parse my time string, time tuple, right? This is exactly what worked for us, at least for the first 2 strings in this format. So let's hope it'll work. And then my float data is I'm just applying the float type casting to each x in my data string, right? That's just longitude, latitude, longitude, depth. They were all beautiful floating point numbers. We knew it worked last week for the whole thing, so let's stick to that. Then what I'm going to do is I'm going to append to my float data this my type time. So the last column is going to be my type time in seconds since the 1970. So then finally, my accumulator list, which is empty in the beginning, I'm going to append to that my float data, right? So it'll have all the floating point types for everything. So this is all in a try. So I try to do this whole thing, and if it fails on a type error, then I accept out. Otherwise, we'll see what happens. That's basically it. No. So the star means it's working. So depending on your machine, it'll take a few or less, more or less. So now I have 2106, excluding the last empty line. So it all looks good. Everything was sparse. So let's just take a peek into the first 5 elements. Looks beautiful. So this is our timestamp in the last field in seconds. So now we're going to be good and wrap all of this into one function because we will call this later. So it's just get long lap mag depth times. And it just takes a CSV file, and all I've done is put the open stuff, everything all in one place, all the imports. So it's nice and clean, can be called elsewhere. So and then I have to just simply pass this text file to it. So I'm rereading it. It's done, and I'm outputting a NumPy array. So I can ask what's the shape of this NumPy array, right? So all looks good to me. Okay. So then what we are after is the inter-occurrence time between earthquakes, right? Because we want not actual time, but the time between occurrences. So for that, we just do a tiny list comprehension. So I'm going to pass it a sorted quake times, because the actual recording of events in New Zealand's GeoNet server is not in the order of occurrence of earthquakes, because they have sensors and there's people looking at things and stuff. So it'll be in different order. Recording order is not the same as occurrence order. So we have to do sorting. But if you give it timestamp sorted things, I just want to do a simple list comprehension by taking consecutive, quake times of 1 minus quake times of I minus 1 for I in range 1 to length of quake times. So I just look at consecutive things and take the subtractions in the right order. And I'm done, basically, right? So if I do, and remember, sorted is how you would take an array, and you will get the sorted list of it. Because if you don't sort it, you will see that they are sort of not even in order. So now I have my function, interquakes time, sorted my processed array 0 through 4, of the 4th column, which is just the timestamp. So I have my sorted inter-earthquake times. And then I do the same thing for all of it, right? So I put a colon, that means it's the whole data, all the rows, and now I get 21,015, which is 1 minus the previous one, inter-earthquake times. Is that clear? Yes. Yeah. So then we basically do this. So we look at the first 10, looks all right. Now we're going to model this. So if I take dot mean, so this tells me the mean number of seconds between earthquakes. I mean, Kiwis are like as close as it gets to Japan in the English-speaking world, right? Because they're in the ring of fire, and it made my daughters really brave. Because I was freaking out, because we had a huge earthquake, in 2011. I mean, we had like continuous earthquakes and aftershocks for nearly 2.5 years, right? I mean, it's not an easy thing to live with, because everything suddenly starts shaking and you have no control over everything. So anyway, yeah, so the children are probably better at anyway. Sweden has no earthquakes, right, and it's rising, so I'm really banking on it, because when there's global warming and the sea levels rise, I'm like, yeah, we'll just shoot everyone that comes here. No, just kidding. Yeah, winters really make up for it, though, I should say. So that's variance and the standard deviation, and then we can do it in seconds, right? So we just divide by 60 to get it in minutes. So it's about every 24 minutes. There's an earthquake on average. Standard deviation is about the same as the mean. Okay, in minutes. So this is our model, right? So we said x1 through xn is IID exponential lambda star. And then we have our observations, lowercase x1 through xn, because that's realized. It's one big sample we have. And then in this array interquake sex. And then my statistic, right, that has all the information in beta is just the sum of xi's. We saw that, because the maximum likelihood estimator only depends on this. So this is called minimally sufficient statistic for this estimation problem. And then that's it. So this is this number. The minimal sufficient statistic is what? 30,283,951 seconds. So we can get a quick look at the shape. So let's look at a simple histogram of this inter-earthquake time. Voila, it looks like an exponential, right? The shape is nicely decaying. And so, well, let's try and see how well the exponential does. So lambda star is the unknown, and we're going to hunt it with lambda sub n hat, the estimator. And we know that's just n over dn, so we just take the sample size, divide by the total, and we get this rate estimate of 0.00069. And remember, when the rate is really small, this means the exponential is pushing it far away, and that's how small the seconds, the rate in seconds have to be, so that the mean is around 24 seconds. So yeah, so this is our minutes, and this is the number of seconds. So then when we take so this as point estimate, we're calling it our best guess in seconds, best guess sex. So 1 over best guess sex is the same as the sample mean, because all we did is invert the sample mean for our estimator. This one is also very simple, like the Bernoulli, which is the mean itself, and this one is the inverse of the mean. So now I'm just dividing it by 60, so I want it to be in minutes instead of seconds. Just for, so we call this interquakes mins. And then let's ask what is the lambda star in this unit, right, in the minutes time scale. And now the best guess mins is 0.0416, right? So then if I ask what's the mean, it's 24 minutes, and 1 over the best guess mins is also 24. So, I mean, the point here is that the rate is actually coupled with the scale of observation. Right? So the rates in minutes is different from the rates in seconds and so on. So there is a notion of 1 here, right? 1 could be minutes or seconds. The scale. So here is yeah. So if we just multiply by 60, we get everything back from the minutes back to the seconds world. So here is a count histogram for interquake times, but this is now in minutes. So this is a little bit easier to interpret, right? Because minutes is, I don't know, easier.
And the timing, the timestamps for the earthquake, is that when the earthquake actually happened, or when it was registered at the Seismic Institute?
Well, I don't know. I just went by the title. One said origin time, and the other one said something else.
Because I mean, if you have this kind of narrow time intervals, it could actually.
No, I know. I exactly know what you're asking. So they changed all their fields since I was looking at this a while back when I was teaching PV engineers. So, like if you look at the header line, it says origin time, and modification time. So I'm assuming modification time is when humans modified it. Origin time is the actual origin time. I didn't go deeper into the docs, but there's no other time information anyway. So I think that's correct. It's the actual time of the earthquake.
And then why do you think it's exponential? Why do you think it's?
Why do I think? I mean, I don't think it is. It's just a good model, right? Because currently we just have only seen uniform and exponential and Bernoulli. And normally inter-arrival times, inter-event times, the first thing you would go after is exponential. And also we looked at the histogram and it looked like it was, so it's a reasonable. We will later on do non-parametric estimation directly on this, I think, or at least you'll know how to do it. I mean, what is non-parametric estimation here, right? So non-parametric estimation here, so I constantly, So non-parametric estimation here would be just taking all of the data, all the inter-earthquake time data, sorting it, and putting this jump function, right? And you can directly go after the, yeah, we will see this, so let's wait. So that's an infinite dimensional model already. Uncountably infinite dimensional model. Okay. Oops. How do I get out of this? This X?
Yeah.
Yeah. Thanks. Okay, some pointers on plotting in Sage Math. So I'll just sort of maybe let you read this. There's a lot going on. There's so many different things you can use. I don't have any kind of, what do you call it, favoritism. I use whatever works. So matplotlib is really good. In fact, PyLab is actually sitting on top of matplotlib. So, we explore these galleries and stuff because often, especially in data science land, you will want to make nice presentations to impress your managers and so on, right? So this one's, this used to be nice. So let's make this, yeah, so the numbers are too much. So let's make this 10. Okay, so you can play around, you can have multiple plots, and so I'm plotting. This is pure matplotlib, right? I'm plotting T with T in whatever red color dashes and whatever blue squares, and so there's a lot of lingo, some symbolic things. So you can get into all that. If you hit that gallery thing, you will just be exploding your brain with so many beautiful plots, and then the source code is right there, so you can click and see it. So what I wanted to point out is you may want to superimpose one of the plots on top of your histograms and stuff. So you don't need to leave PyLab land for this. I basically put that matplotlib plot as a pylab.plot because it's a superset of matplotlib or some intersection thereof. So you can get whatever, some plots superimposed on histograms and stuff. So it's sort of nice too. And there are links to animations as well upstairs in the gallery. So if you want to make more animations, you will see later on. You can do all of that as well. So yeah, just try this later. This is just a bit more exercises on symbolic manipulations, right? And so take this Sage Math feature tour because I'm just touching almost nothing of Sage. I mean, I'm giving you the basics, I think, like fundamental number systems, but it's just like opening the door a tiny bit. Right? There's a lot in Sage Math. It's literally 100 open source packages, various things that are here. These videos are really good. So you have, a lot of group theories, calculus, dynamics, and most importantly for me, graph theory and structures, random structures. I really get into Sage quite heavily to even develop the mathematics for me, because I build my intuitions on what I should define and propose by playing around because if you just do by hand on the blackboard, it's good to start, but I can't explore very, very large graphs and ask, how should I go about proving some theorem or build my intuition? So modern maths is done like this, I would say, where you actually use something like Sage coupled with pseudo-random streams to, if you're doing more probabilistic models. With all the machinery it provides around symbolics and so on to build intuition. Even for maths. Okay, so let's get into the next notebook now. So this is number 10. So this is Markov chains. So I'm going to have a quick attendance check. This is not very sophisticated, but so I'll basically look for people that are in at least one of my random photos. If they say they want, I mean, I'll remember most of you, of course. But there are others that are registered that I don't know them, right? There are like people from them. They yell at me in emails saying, "Can you do this? Who are you?" Anyway, couple interesting guys from Meetup, but I keep them engaged. But I never see them. I don't know what they're doing. Maybe it's a bot. Okay, Markov chain is a very, very important concept. What is different about Markov chains is that, see, so far what we've seen is mostly dependent random variables, right? I mean, independent random variables. So this IID assumption, we want to break that. I mean, we want to relax that. So Markov chains are the simplest way to relax that, right? And I'm giving you the absolute simple Day-3 Markov chain from Wikipedia called the dry wet chain. That's enough for the basic concepts, right? But Markov chains themselves is a full semester long course, even at the undergrad level, like 400 level. So what is mainly Markov chains allow us to do is, relax this sort of independence assumption, right? So we've seen only independent and identically distributed, right? But there's another notion called independent and not identically distributed. This is also not Markov chains. So what is this? This means I'm saying I observe my data, x1 and y1, and x2 and y2. This is some cooked up example. And it's such that, the xi's are IID according to some density f of x, semicolon, say theta 1, some parameter or vector of parameters, and yi's, all the yi's are IID according to some other density, say g, right, of y, semicolon, theta 2. So this, this is saying all of them are not identically distributed as the same f, but some of them have this density and some of them, trouble seeing downstairs, and some of them have this density, right? So this is independent and non-identically distributed. All of this likelihood theory, everything we've seen will carry through. Expressions will be more messy, sure. But if it gets too messy, no sweat. We can always do numerical heuristic optimizations, right? So, but we can always write down the expression because the likelihood for this independent and non-identically distributed data, right? What will that be? The likelihood of all xi's and yi's as a function of theta 1 and theta 2, right? Will just be the product of the f's, right, over xi's, and multiplied by g of yi theta 2, right? So that's how that will work. So there's no big deal, and this is a large class of models. But what we want to is go beyond that. We want to have some kind of dependence, right? So Markov chains allow us to have dependence of current state of the process or system, dependence of future state on current state, right? That's the simplest kind of dependence. And we saw this already with the frog example, jumping around lily pads, and in each lily pad there was a die the frog rolled to decide which of the adjacent lily pad it'll hop to, right? That's dependence because any lily pad the frog lands in, it has to use the die there to decide where it's going to jump next, right? So the immediate future state's probability depends on the current state. That's essentially encoded in the Markov chain, right? And the way you say this is why we introduce conditional probability. So the way you say that is probability of so the way you say it is probability of xn plus 1. That is the state of the system in time n plus 1. So there's a natural notion of time here, just like a sequential notion we had x1, x2, x3. So the n plus 1 random variable, given all the random variables before, since the beginning, is only going to be this conditional probability. It's only the probability of xn plus 1 given xn, which is a nice simplification because you know, it ignores, you can ignore the history up to where you are, right? So that's a you know, so-called Markov property, and this is not too strict. You know, you can have finitely many states in the past, like not just where you are, but where you were for the last 10 spots. Also be taken into account to determine the probability of the next step. That's also Markov. That's called higher order Markov. But it's the same idea, but we'll just develop with this simplest first order Markov property. So this is a bit of formal definitions. A Markov chain is a sequence of random variables, x1, x2, x3, dot, 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 with the Markov property, namely that given the present state, the future and past states are independent. Okay, so that's what this is basically saying. Yeah, the future is independent of the past, which is going from xn minus 1 to all the way to 1. Only the current matters. Okay. So then the way you would encode this probabilistically, what is a probability model? It's this matrix called bold P. It's called the transition probability matrix. So all it tells you is, you know, so the first thing you need to encode is what are the possible values that the random variable can take, right? So remember, this is our math BBX, right? This math bold font X. So let's say we're only going to look at discrete state Markov chains. So discrete state Markov chains are ones where you have either finitely many states or at most countably infinitely many states. That's why this matrix goes like this. So I'm calling the states without loss of generality 0, 1, 2, 3, and so on. So the, you know, all the lily pads, it's like an countably infinitely many lily pads in this universe that frog lives in, and each one has a label. So it's 0, 1, 2. Because it's countably infinitely many, I could have an enumeration scheme by definition. So that's my state label. Okay? So I have all my states listed that way and this way. So P00 tells me what's the probability if I'm in state 0, I jump back and land at 0, right? And P01 is the probability I'm in 0 and I jump to state 1, okay, and so on. So now the sum of these rows, each row's probabilities should be 1, right? Because I have to do something. That's the axiom of probability, right? The first one. And then wherever I am, so this is probability of going from 1 to 0, starting from 1 and ending up in 1 and so on. This is exactly, if we truncate it by capital N, where capital N is at most like, you know, 100 million or more, or less than, I don't know, definitely a trillion, then we can actually take the entire world's OpenStreetMap, okay, this is connecting back to the lectures from the geospatial module, and break each chunk of this roadway into small fragments, and each fragment can be a state, and then the you know, and the map itself will tell you which state allows you to access which state, right? Because the roads are all. So this is I don't know how many of you were in that module, but so it's a direct connection to Markov chain representations using GraphX of OpenStreetMaps ingested using osmosis, right? This is what we were trying to do. That notebook is almost done except the last 2 or 3 cells, and if you can solve it, then you can be a chapter author for us. Dylan is busy. I need like 3-4 hours, lots of tequila. So I'll get back to it after I grade everyone, but the hop is really not that far from what we're doing to essentially looking at all the trajectories of about a couple million Scandinavians, cell phone records for the last 2 years on OpenStreetMaps of Scandinavia, right? It's right there. Okay, then this is the other one. So then the state of the system, that how do we keep track of the state of the system at the nth time step? It's described by what's called the state probability vector, P super n, right? So this vector has a probability of being in state 0 at time n, in state 1, probability of being in state 1 at time n, state 2 at time n, and so on. So this possibly countably infinitely long vector, this will be of length n if the number of states is only n, or m, let's say. This vector is the main object of interest because that describes the state probability of the whole system at time step n. Okay, and then P sub I super 0 is called the initial probability vector at the convenient initial time of 0. So what does the system, where does the system start when you start modeling it, right? So in a frog example, if we know there's only one frog, but we know it's in that lily pad at time 0, then we basically put a 1 in that state. Say the state is 83, the lily pad number 83. So we put a 1 in 83 and 0 everywhere else. Let's say there are only 100 lily pads, right? So we put 0, 0, 0 and 1 at 83 and 0, 0 everywhere else. So that's a way to specify the initial state probability vector. But then if we don't know that and the frog has been jumping around forever, then we can try and guess, right? Or, maybe if every lily pad is connected to every lily pad, a reasonable guess is that the frog is uniformly found, equally likely to be found in each of the 100 states. So then we put 1 over 100, 1 over 100 in each initial state. But this is where you would bring your prior information into the system. So now, with those two things, we're pretty much on our way to go because we just need a mechanism to get P, the state probability vector, lowercase p super n, from the current state probability vector, which is lowercase p super n minus 1. And this simply comes from multiplication, matrix multiplication, as we will see. So this is our little weather model. We're just looking at the simplest first example in Wikipedia, simple weather model. So here we just have two states, sunny and rainy. So I'm calling it dry and wet. Because it can be sunny when it's raining, so I'm kind of into language, like dry or wet. So yeah. So then the probability transition matrix P is this for their little example. They pick these numbers somehow. So 0.9, 0.1, 0.5, and 0.1, and this is called the flow diagram, the transition diagram or the flow diagram of the Markov chain. So it says when you're in sunny, you go back to sunny with probability 0.9. So the first state is sunny, say 0. And the second state is rainy, which is 1. So if you're sunny, then you go to rainy with probability 0.1. And if you're rainy, you go to sunny with probability 0.5. And if you're rainy, you remain rainy with probability 0.5. Very nicely encoding the example here. So the transition probability matrix is also called a stochastic matrix. So what's the idea is we want to predict the weather. So initially, let's say it's sunny. So this is the sunny. There's 0 chance of being rainy today, and we know it's a sunny day. So this is how you'll start the initial state. And then to get the next state, so I use lowercase bold p, but they use capital X, which I don't know. I don't have time to edit Wikipedia right now, but this, normally in math books, this is bold p because bold X is like the state, and you don't want to mix it with the probability of being in that state. So, but anyway, so you just left multiply this initial state probability with the matrix like that to get the probability of the states in the next time step. And if you have to do this arithmetic by hand to see what's really going on. 1 gets multiplied by 0.9, and then 0 gets multiplied by this, right? And then 0 gets multiplied by this, and so basically, this whole first row gets preserved, right? So you're just reporting the first row. But if these numbers were non-zero, then you're actually looking at, how the probability mass flows through these multiplications. So that's what, and then this is you can also look at it this way. So you take, so to go directly to the second state from the first, you have to multiply by p twice from the right. So that's just p squared. So you can just do 1, 0, p squared. And this tells me what the system will be at in 2 days, prediction for 2 days, and so on. Okay. So this is the general rule for day n, is xn is xn minus 1 times p, or xn is x0 times p to the n. Because, why is it p to the n? Because the transition probability matrix itself is not changing in time. That's by assumption, right? And when I was showing you guys about this old Bailey online, this digital humanities data, it just takes this Markov chain theory to like some crazy, jazz, right? It's the same idea, but there I'm actually allowing the transition probability matrix for the evolution of punishments for offenses in English law to change every 3 years. So for the first 3 years, I'll have one transition probability matrix, which I'll estimate from the data. And then for the next 3 years, I will allow the transition probability matrix to be possibly different from the previous 3 years, because we know the law was evolving in England, right? So if I have transition probability matrix that are time varying, that's okay. All of this theory works. It's just that instead of multiplying by, p squared, you do p times p prime times p double prime or whatever, different p's, right? And you cannot, you need enough observations to estimate p, but as long as your windowing is right, in some sense, you can have time varying transition probability matrices. That's no biggie. All the theory works that we will see for this time stationary process works. And the next thing is steady state of the weather. So what happens as n goes to infinity for the state transition probabilities? So will they evolve to some fixed vector, right? And do you guys remember when we were exploring the eigenvalues and eigenvectors, I was showing some convergence of the eigenvalues and eigenvectors to a particular point. That's, again, the stationary behavior of this process. So, under some regularity conditions, the matrices will converge to, Okay, so then this is the Google's page rank. So remember, when these things get too big, citation rank. But yeah, Google's page rank is the same idea. Oh yeah, it's here. So there, you just, you have very, very many states, maybe all the web pages. And then the links, tell you from which web page you go to which web page. And then the model is just, you choose all the outgoing links from your current web page with equal probability. So if you have 823 outgoing links, you choose 1 over 823, one of them. And so the sort of frog or whatever, the random surfer jumps like this. But the magic is that with probability 0.15, because the random surfer also tosses a coin with probability 0.15 of coming up heads. And if it comes up heads, the random surfer will jump to any one of the possible websites uniformly at random. So you never get stuck anywhere to these places where you cannot come out of. So that's the basic idea in Google's page rank. And then the stationary distribution of that Markov chain is the ranking algorithm. Right? And then recall from our lectures from the previous modules in big data is we can find the stationary distribution using Pregel programs, right? Distributed vertex programs where each vertex passes messages to its neighbors and everyone updates the messages until they reach convergence. That's basically, again, this Google model of bulk synchronous parallel programming. You remember this? We covered this, right? This was in GraphX. This was before MapReduce, right? MapReduce was new. So this is the Pregel model. So all of this is completely connected because you need that technology when you cannot represent your matrices in one machine. So then you basically take the states, throw them in different machines, and then handle and then pass messages between vertices. And so you can get the stationary distribution using that. It's just a recall. Okay. So here's our little example now in a more tight notation. That's in sync with what we've been doing before. So our state space, what values the sequence of random variables can take is wet and dry. We can call it 1 and 0, and then and this is basically the flow diagram for us. This is just from Wikipedia's numbers. So that was their matrix. So we can go from dry to dry, and which they call sunny, and wet to wet, and 0.5, which they call rainy. So it's exactly the same. So for me, the ijth entry of the matrix is lowercase p(ij), and every row sums to 1. And how do we represent a matrix in Sage? We played with matrices before when we're doing modular arithmetic. So I'm going to have my matrix to be RR in the multi-precision floating point real world, and I'm going to have a list of lists telling me what the rows are, right? 9/10, 1/10, 1/2, 1/2. So I could have used QQ instead of RR. QQ is the rational field, but I'm going to use the real field because I want to do floating point arithmetic. Later on, I want to drop into NumPy. So P01 is just, it's just giving me the this entry. So it's always good to know your parents, especially for matrix type. So this is a full matrix space of 2 by 2 dense matrices over the real field with 50 units of precision. That's what you're operating on. So now predicting the weather with our dry-wet chain is our problem. So my initial state probability vector P0 is 1, 0 because we're starting on a dry day. And then the next day is just basically by multiplication, just like what was in Wikipedia. So here is P0, and then I multiply P0 by P, and I get the next entry. So it's exactly the same. I do P squared, and I get this. So I'm just literally marching. This is the Sage mapification of Wikipedia example. So now I can disclose the probability vector at time step 2 is P2. And I can generalize this, n equals 3, and so this is the same. So if I have a wet day, it's different, right? So if I started my initial probability vector for starting predicting the system from a wet day, you see after 3 days, the probability of being dry is lower than the probability of being dry if you started from a dry day. That's kind of the point. But then, so here's, so yeah, we're just doing this so that we keep track of the number of days and then the state probability vector as it evolves from these left multiplications with the transition matrix. Okay, so now let's do an interact. I don't know if this is going to work. Oh yeah. So what I'm showing you is if I started from here, I'm going to go here, right? This is, you know, if I started with 1, 0, so a dry day. If I started with a wet day, I'll start here. And then at one time step, my transition probability vector moves here because this is a 2D thing. It should really be square, but I'm just showing it as a rectangle because. And then you know, in 1 day, this guy moved here, and in 2 days it moved here. So if I increase the number of days to 4, see it's moving closer and closer to this black dot. And that's kind of the moral of the story. The black dot is going to be the stationary distribution of this transition probability. The state probability vector. So then if we keep increasing it, you know, it's going to not budge. It's just going to be sitting right on top of the black dot. So that's called the steady state of the weather in a dry wet chain, right? So the steady state is bold S, and it's defined as the limit as n approaches infinity of the nth day's state probability vector. That's all this is. Right? So what happens as n gets larger and larger, and there is sort of a straightforward way to look at this. So I'm interested in finding if there is a stationary vector S such that its rows sum to 1, and when I multiply it by P, it remains unchanged, right? So S times P is S. That's called the stationary vector. So is there something? So how would I hunt for it? I just define it, that matrix, right? So P is here. I multiply S to P. Sorry, I do S times P equals S. That's the equation I want. So then I basically multiply it by I, and then I subtract I, and then I can solve for it directly. Okay. So here are my conditions. So negative 0.1 times S0 plus 0.5 times S1 is 0. And since they're probability vectors, we know that S0 plus S1 should be 1. So solving this pair of simultaneous equations gives me this, right? So we can do this symbolically as well, but this is a straightforward equation solving, right? So then we know that S0 is 5/6 and S1 is 1/6. And this unique pair of numbers, when you multiply it with P from the left, it will come back with 5/6 and 1/6 on the right side. And that's exactly the idea of eigenvector whose eigenvalue is 1. Right? This is something we saw in linear regression in Hari, right? So in conclusion, the long-term 83% of days are dry and the remaining days are wet into this model. Right? So to solve for this in stage math, there are two ways. You can solve a system of linear equations with solve, the solve method to get the bold S, or you can obtain bold S via eigen decomposition. Right? Solve system of with solve. So this is annoying, and this should be math BFS. So sorry about the typos. Okay. So anyway, I'll sort of not get into eigen decomposition because not everyone probably have linear algebra 100, 200 level. So here is the method 1. You just basically set your matrix as P, and then you set your identity matrix. And 2 by 2 identity matrix, and you're just implementing the formula P minus I, and S0 and S1 should be declared as symbolic expressions, variables, and you set your equations. These are the equations. And here are the list of equations you want to solve. And you just have to make sure it's a transition probability. And then that pops the answer, right? You can also do it this way because equation 1 equals 0 is redundant. You can also solve it simply this way as well. So we've got some redundancies. So that's just how we use the state symbolics to solve those equations to get directly to the stationary distribution. Method 2, I don't know. You should really. So this is what we were playing with before. Remember? Spend 1 minute on this. This is remember this interactive thingy. So this explains again what is A times V, what are eigenspaces, eigenvectors, and so on. So we started seeing that when you start with the V, it'll approach somewhere. For Markov chains, it's quite nice and linear. Okay. So just get into these things if you want to. And these Khan Academy videos are really good. They will let you go down to things you don't know and go up to things you. This is a good place to start for eigenvectors and Khan Academy. Okay. Here is my full matrix P, and this is my eigenvalues, and this is how you would symbolically do this. I have my eigenmatrix left, and my left eigenvector, and okay, so then checking when we left multiply by left eigenvector of the eigenvalue, we get the output space, and we can do the inverse, and making sure the eigen decomposition of P is in dp. I mean, I'm just sort of doing. So you can do this, and this will work for fairly complicated matrices, especially if you have coefficients, but not the dimensions are too high, of course. So it's very useful to have under your belt. And then lots of large problems can be projected down to lower dimensions to have qualitative understandings. Once again, the eigenroutines will be handy there.
Sorry, one quick question. Should we think about the stationarity distribution as if you pick sort of a random state from a Markov chain has the probability of having wet or dry? Would that make sense?
So yeah, that's right. So one way to think about it is, let's say the whatever world operates like this, dry and wet days. It'd be interesting to do this on Singapore actually. So then the idea is that you go somewhere else and then you come back and you're entering the system with no information. Then because the system has been running for a long time, it's safe to bet that you will find yourself in this, the system is at steady state, so the chance you will end up on a dry or wet day is the stationary probability. Yeah. And often in bioinformatics, this whole field called phylogenetics, and they take DNA sequences and then they will try and build ancestral relationships of various species that they take these sequences from. And then what they have to do to model the divergence time between species is to have a model of mutation of how the DNA sequences go from, say, A to C and G and T. There's 4 sequences. But then they won't know what the original top ancestral most recent common ancestral DNA sequence was. So what they will typically do is they'll assume that that was a stationarity of the mutation model and use that stationary distribution of the mutation model as initial conditions for the most recent common ancestor. And then they will set the whole likelihood function. It's a bit field specific, but it's, yeah, exactly the same thing. What can be done when you don't know what to do. So I don't know if this URL lib2 is going to work, so try it. We're going to pound my math department in New Zealand. Let's see. It's pretty good right there. Let's see, it should work. So this will basically get this data we sort of kept for a while. So it stops at 2012 now, kind of when I started consulting for industry and stuff. But it has 25,044 records. And if you look at it, it starts from 1943, August 2nd, which is when the airport in Christchurch had this weather station recording events. And then if you look at the last, it stops at May 6th, 2012. Okay, and it gives you the precipitation, rainfall millimeters. So you can kind of do this interact quickly, like this interact actually. A little time to get it going. So you can choose the start date and see, you see, increase the number of days all the way from the beginning, let's say, to all the way to the end. And you're seeing now millimeters of rainfall in Christchurch for each day. So that's, I mean, okay, it's interesting. So now I just wanted to look at some random bit. Okay, 200, 210 looks like this. So then what I wanted to do is just grab the rainfall measurements. So I'm just list comprehending the second element. Right? I'm just doing it for the tiny list before I do it on the full thing. And then I can ask whether the rainfall in precipitation is more than 0, which to me is wet or dry. Okay, that's how I define wet or dry. And so now I cast the booleans to ints, so I get zeros and ones, right? Sort of in my Bernoulli land now. I mean, so you could take this data of zeros and ones and do a Bernoulli experiment and say, if I just go in, what is the probability that I'll find? And if it's IID Bernoulli with unknown theta star, you will just take the number of ones and divide by the sample size and report your bias, right, or your theta. But we're going to do more. We're going to now do a Markov chain instead of the Bernoulli IID experiment, right? So grab all the days of data from the start. It's here. So I'm basically now going through my whole thing in this Christchurch rainfall, casting it to int, and then I'm also recording the day number this way. Okay, so all days data is like this. And I guess if you want to, yeah, so all days data is exactly the structure. Oh well, let's just quickly look at Okay, so it has the initial day is 0, second day is 1, and so on. And then whether it's dry or wet is zeros and ones. Okay, so wet is 1, dry is 0. So if I look at -3 to -1, so there are 25,041st day is dry and 25,042 day dry, because in May in Christchurch 2012, yeah, summertime. I get completely confused with northern and southern hemispheric summers and winters, so I don't want to go there. Because you know, white Christmas has a completely different meaning. Christchurch, I have so much pollen in Christmas. I'm not kidding. It's whites in the air. So this is basically, yeah, let's try this interact out. And yeah, so it gives you, so yeah, it lets you choose a small set of days to initially play with. So we were just trying to, you know, so then you can increase it if you want, but I highly recommend just keeping it small initially, and because we have the full data anyway. So that gives me my dry and wet days. So if this is loaded into the cell days data function. And you know, all of this is not mysterious, right? I have this new thing here called global. This is the new keyword. You guys know pretty much everything else to understand what's in this interact now. But this global thing sets a global variable that I can create inside from the user selecting it interactively. And then that's ready for me to play with. I know it's kind of, Ross, why are you doing all this? I don't know. I like to kind of roll my own on simple things. And you guys, the reason we developed all the concepts in this order is so that, you know, you should be able to understand all of this now. Everything there, loops, conditionals, list comprehensions, it's all there. So this way, you know, you have very, very nice control over how you, as a data scientist, interact with the data, you know, every step of the way. So you don't have some, you know, Microsoft's or whatever, Google's proprietary or IBM Watson, you know, magic black box and stuff. You don't need to go there, really, if you go, you know. Unless your executives get bonus packages part of the deal. That's a different problem. So anyway, yeah, here you go. That's basically my data I'm going to play with, and then I'm going to look at just the dry and wet stuff. So that's that, and I should have 99 guys if I took the default. So now maximum likelihood estimation of the unknown transition probability. So this is basically for Marina mainly, right? So that whole problem I said, you know, you have trajectories, co-trajectories. That means, you know, people moving on, you know, Swedish roads or whatever. You break the roads and pathways into small pieces so you know where people are moving. So that's like zeros and ones, dry, wet, right? So instead of zeros and ones, you label each, you know, 50-meter length of the road or whatever into integers, 0, 1, 2, 3, C. So then people are moving from one integer segment, one integer state to another integer state. That's how you encode the trajectory of one individual. But you have multiple individuals, so that's called a co-trajectory, right? So you have sequences, just like 0, 1 sequences, you have trajectory sequences, but the integer labels will be much bigger, I mean large space. And then now what you want to do is somehow, in this case, we want to infer the transition probability matrix. And again, there you want to infer the transition probability matrix. You want to understand how a certain population of humans with their socioeconomic indicators are moving in the roadways, or how do they normally move on a weekday versus the day of the Swedish the terrorist attack day, right? There was a day where the whole transportation was disrupted and so on. It would be very different movement patterns. So you want to really understand these things in subtle ways so that you can anticipate and plan for emergencies, whatever these guys do. So it's the same basic ideas from here, and later on after lunch we'll get into hypothesis testing. So when you couple these things, we should be able to do things that Pearson wanted people to be doing in 1901. So this is the basic idea. So this is the true model, or just the given model. But if we don't know what the actual values are, we will encode it by this, because for Christchurch Aero Club data from NIWA, which is New Zealand's National Oceanic and Atmospheric Administration, basically. And you have these probabilities. You say, I don't know what it is. I would ideally like to put a star on them, but yeah, they're just thing we're after. So then the maximum likelihood estimator for the entire matrix is p hat. It just has a hat on all these unknowns, right? This is a random stochastic matrix, so it's going to suck the data and boom, produce a random stochastic matrix at you, okay? And we can even have confidence intervals on this random stochastic matrix, which means trap it into matrix spaces. But for now, we'll do point estimation. So it's the same idea. The likelihood is simply a function of the unknown parameters given the data. So what is the likelihood for the unknown parameters given the data? We basically, the first thing we realize is we only need P00 and P11. Although there are 4 parameters in the matrix, the other 2 can be gotten by 1 minus the diagonal entries because the rows sum to 1. So there's only 2 parameters effectively here. And so similarly, when you have a very, very large matrix, a n by n or m by m transition matrix with m very, very large, then basically it will be m square minus m entries will be this, the parameter space, the size of the parameter space, right? Okay, so this is basically the likelihood function. We basically want to know what is the probability that you start at time 0 in x lowercase x0, at time 1 the random variable is lowercase x1, and so on, right? What did the random variables actually take as their realizations? What is the probability of that path? That's basically the likelihood, or it should be proportional to that. And I don't want to go through this. I checked it last night again. It's right. So I'm just mechanically marching through this, but please go through it to really understand every step. So there's a lot of specific assumptions that are being made in each step. So I really wrote it out. In the end, what you'll get is P00 to the power of N00. N00 is number of transitions from state 0 to state 0. Lowercase n01 is number of transitions from state 0 to state 1. And n11 is state 1 to 1, and n10 is state 1 to 0. So only these 4 transitions, 4 possible transitions between 2 states, the count of them, the frequencies of them, are the minimal sufficient statistic for this likelihood, for this model. You don't need anything else, you see? And this is kind of our little pitch for this grant we wrote together in a big hurry last week on top of all this. So the idea is that this is a new thing, right? Remember Michael Jordan's talk on privacy and math stats and decisions? So this we are calling privacy by mathematical design of the experiment itself, decision procedure itself. So what will be really good, possibly for Swedish law and policymakers and stuff, is even the decision makers like statisticians in government and those in other agencies should not be allowed to see the trajectory data directly. They should only work with minimally sufficient statistic of the trajectories. Because you can do quite a lot with this. So this way we can ensure the privacy of a citizen, basically, right? And we can even allow simple things like if a particular Swedish citizen says, I explicitly reserve the right to not be seen within 1,000 meters around, I don't know, nightclubs or whatever. Maybe they do some naughty things, I don't know, or maybe they don't, right? Or maybe they'll say, I don't want to, I don't want to be identified anywhere outside the planet. That's okay. So these things can be formally brought into all of these expressions. And so now you can, basically using these ideas, you can say the data, the people that consume the data to even make policies in government will not be allowed more than what each citizen wants them to see, right? So all of this comes through the same basic ideas. All right, I just say we have the mod likelihood function, and you estimate it, and this is all you can walk through it. So in the end, what I'm saying is that the probability estimate of going from state 1 to state 1 is given by the number of transitions from state 1 to state 1 divided by the number of transitions from 1 to 0 and 1 to 1. It's really that simple, right? And it's the same way for P00. This is the other thing we're hunting, right? P00 is just N00 divided by N00 plus N01. So it's easy peasy at the end of the day, right? Completely intuitive. It's enough to start, right? So now these are just likelihood expressions, so you can just evaluate them and solve them. And what I did upstairs is right. This is at least by Sage. So now I have my transition data, and then I'm just making I'm just bringing that make predict from before, so I can count things. So here's my transition counts, and this is for the tiny data I made. And then here is my n00, n01, n10, and n11, right? So I can use this function called transition counts, and it'll just report me what these 4 numbers are. And that's all I need for that's all the whole sequence of zeros and ones boils just down to these numbers for the small data set I chose and interact. The 99, right? So this should sum to 99 or 98. Okay, so here's a function to make the transition counts. And then I can apply it to all days. And here's my transition counts between 0, 0, 0, 1, 1, 0, and 1, 1 for all of the data. So now my matrix P hat is simply the MLE matrix. And this is like 1951 statistical theory, right? It's by Billingsley. It's a really beautiful book. It's a nice red book. You should read it because he explains it like in kind of English. I also like math books from 30s, 40s, and 50s because people are sort of explaining maths like normally. Now there's so much formula, it's too much. I can't take it. But yeah, old books are great. Yeah, so this one, now I'm just defining a function to return the MLE tuple P00 and P11, and we're almost done. So now that gives me my maximum likelihood estimate. So P00 is 0.75 for my Christchurch weather data, and P11 is 0.52, which is quite different from the random numbers or the numbers chosen in the Wikipedia example, right? And you can kind of compare this with if you did a Bernoulli, what will it be, and so on. So the point here is now what I'm doing is I'm trying to animate using GIFs that were constructed with other Sage animations of the maximum likelihood estimate as the sample size increases. So I'm pretending that I was in New Zealand from the 40s, or this estimator was, and it's giving you this P hat, this matrix P hat, as time evolves. So it's using more and more of the data. So it's like the running mean example, right? Running estimator. So with this sort of running estimator, as sample size increases, so we start here. These are this sort of animated GIFs in loops. Unfortunately, they're not synced. So as sample size increases, it starts from here. And this is actually in motion. This red thing is currently in motion. So it starts settling down, right? It's actually moving. And it'll loop back and start from here and take this path as we increase the number of, there you go. Right, it's the P00 and P11 estimates. And it sort of settles down. And in the same way, this is the log likelihood function of the P00 and P11 estimates as we are moving. So, do you guys like these plots?
Yeah.
There's a lot of time. I actually was getting into so Jenny Harlow, this is my sort of really brilliant student from New Zealand, and I worked on a lot of this, but it was all done in this old Sage worksheet thing, so it took a bunch of time to redo it. And I was going to show you guys how the animation works, but then, anyway, it's not. So yeah, there it is. So this is the log likelihood value, and then we can, because I'm just basically substituting in the likelihood expression the actual transition counts, and I get my actual maximum log likelihood value at the MLE, maximum likelihood estimate. And this thing just shows us the contours of the log likelihood, and this is where the MLE is. So this is also really nice if you want to get into the syntax of contour plotting in SageMath. Okay, and if you did a Bernoulli experiment, almost done. So if I pretended it's IID Bernoulli theta star, and then I use the same thing to detect, then all I need is the number of ones divided by the total. So that is the, so I was tired. So this should be marked down. So the question is, what is the MLE theta hat of the unknown theta star in this model, right? So you can think a little bit about this. So you have the number of ones and zeros. And how is the Markov chain model fundamentally different from the IID Bernoulli model? Anyway, so we talked about all this, so think about it. And this is how you would quickly get graphs in Sage. And in fact, you can turn this into LaTeX and stuff. So this is very, very useful to use because what I'm using is this digraph, okay? And you can, that's a directed graph library, so you can do very, very cool things with digraphs. Here's a little U-try if you want to play around. This is a slightly different Markov chain describing the mode of transport used by a lazy professor. See if you can hack that up as a U-try. And here is random walks on stage. So maybe we'll start here after lunch. I don't want to rush through that too much.